Okay, good morning, all of you. So, last class we saw the FIR filter, um, and we saw especially what is an all-pass filter and the uses of all-pass filter. Um, we have not seen or we have not done a quiz based on that. We'll have a quiz based on that, and today's class also combined together we will have a quiz. And one more thing I want to certain here is that the quizzes marks will be counted for your continuous violation. So please make sure that all of you write your attempt the quizzes regularly. Okay. Coming back, let's go to presentation mode. We'll be seeing how to implement digital filters. If you have an IR filter or FIR filter, how will you implement it using multipliers and adders? That's what we are going to see today. Okay, so let's go to the presentation mode. Okay. So today we shall see how to implement digital filters. So let's start with our FIR digital filter. For example, if you take x z equal to say 1 plus z inverse, which is the first order um, low pass filter, as we have seen, this how will you implement? This is basically yz by xz, 1 plus z inverse. That is yz is xz plus z inverse into xz. And if you take inverse set transform, this is basically yn equal to xn plus xn minus 1. Now, how can this be implemented? You need yn as output, xn is your input, xn is added with xn minus 1, you put a delay. So here you get xn minus 1. This will be xn minus 1. You add xn minus 1 with xn. You take a sum of adder. So you get yn. So xn plus xn minus 1 gives yn. So this is the implementation of first order FIR filter. This is a first order FIR low pass filter. So you have input xn, you have delay. So using delay and summer, you can implement any filter. You know that. Okay, now suppose you have hz equal to 1 minus z inverse. In that case, you will have xn minus 1. So xn will go here. This xn minus 1 will subtract from this. And you will get yn, and that's implementation of hz equal to 1 minus z inverse, which is the first order high pass filter. Okay, now suppose you have some random hz equal to say a0 plus a1 z inverse plus a2 z raised to minus 2 plus etc. Say am z raised to minus m. If you want to implement this, how will you implement? If I see You take the inverse transform, this become yz by xz. You cross multiply this become am z raised to minus. So yz basically become a0 xz plus a1 z inverse xz plus etc. up to am z raised to minus m. And this can be written as yn equal to a0 xn plus a1 xn minus 1 plus etc. up to am xm minus m. So if you try to implement this, your yn depends on xn and the previous values of xn. So xn you take as such. You take delayed version, say z inverse. This will be xn minus 1. That have to be multiplied by a1. While this have to be multiplied by a0. This is a weighing factor, a0. So a0 xn plus a1 xn minus 1. So we multiply this with a1. Then you put another delay, z inverse. Here you get xn minus 2. You multiply it with a2. Take it. And afterwards, after many iteration, you will reach am. You get x n minus m here. We'll have a delay raised to this. And all these you add together. To get y. So this is the basic implementation. You can draw this some other way also, like you can put x in here. Instead of taking this set to this side, you can take set to this side. So you get set inverse, etc. up to set raised to minus n. Yes, set raised to minus 1 here. And from here, this is x0, or this is a0 xn. You multiply this with a0. This is xn minus 1 basically. You multiply that with a1, take it. Similarly, you do it for so whatever you are getting here, you can add together into a summer, and that will give again y. You can the implementation you can do in your own way, but finally you should get the yn, which should satisfy the equation a0 sigma a n raised to minus n. So n varies from 0 to say m. This is precisely the equation that we have written here. This equation I have written in summation form as sigma a n z raised to minus n, where n varies from 0 to m. So this FIR filter in general can be implemented in this way or this way. Both are same. This way. Now let us come to the case of say some FIR filter. You know that IIR filters are having infinite impulses in the impulse response. That is, Hn is not finitely supported. It can have values from over a large area, not confined to some small numbers. So how will you implement these kind of IIR filters? Let us take an example of IIR filter. Let's take 1 by 1 minus set inverse, which is the common Hz we used to see, where the impulse response Hn is Hn is a raised to n un. Here a is 1, so this is basically un. This is the transfer function of your unit step function. Now h series 1 by 1 minus z inverse. Let's try to represent this as yz by xz. This is 1 by 1 minus z inverse. So yz into 1 minus z inverse is basically xz. So now you cross multiply this, it's become yn minus 1 is equal to xn. Or yn you can write as xn plus yn minus 1. So in this case, you know that output depends on previous values of outputs also. But in the case of FIR filters, output depends on previous values of inputs only. So now let's try to implement this. You have xn is coming. You have yn also. Suppose your yn is here. From yn, you take a delayed version. So here you will get yn minus 1. So xn is coming. Xn is added with yn minus 1 to get yn. Okay. Xn is added with, so this is xn, it is added with yn minus 1, previous value of yn to get your yn. So you can see that there's a feedback loop. So when you have, this is xn, this is yn. So your hz was basically 1 by 1 minus z inverse. Okay. So okay. So let us take some examples of let's take a random structure. Suppose this is your xn and you have yn here, and suppose yn is from here, you take delay, so you get yn minus 1 here. You multiply it with some value, say I'll call this b0, take it here, you add it with this, and finally you add it here also. Suppose you put another z inverse here, this will be yn minus 2, multiply it with say br, and you add it with this, and suppose xn, suppose you put some z inverse here, so that you get xn minus 1, and you multiply it with some value, say a0, then suppose you add it with this, okay. So this is xn, this is yn. So can you tell what comes here at this point? Somebody unmute and tell what will be this W point. What will be the W point? Can one of you unmute and tell what will be at W? What will be the signal at W?
xn plus a0 xn minus 1.
Xn plus a0 xn minus 1. Very good. At W, the signal that you have is xn plus a0 x and minus 1. Now that comes here and it is added with something that is coming from here. Now let us see what is coming from here. Someone else, can you tell what will be at the point wy? This is point y.
B0 yn minus 1 plus B1 yn minus 2.
B0 yn minus 1 plus B1 yn minus 2. Very good. Very good. Okay, let me put this as B1 and this as B2 so that our notation become easy. Let this be B1 and this be B2. Okay. So at y you have the signal yn is here, yn minus 1 is here, yn minus 1 is multiplied by b1 and it's added. Along with that, yn minus 2 is multiplied by b2 and added. So basically at y you have b1 y n minus 1 plus b2 y n minus 2. So this is added together to get the point y, and w and y should be added together to get yn. So yn is basically summation of these two terms. So xn plus a0 xn minus 1 plus b1 yn minus 1 plus b2 yn minus 2. Now this you can write as, suppose you take a transform of this become yz equal to xz plus a0 xz into z raised to minus 1 plus b1 yz into z raised to minus 1 plus b2 yz into z raised to minus 2. So from this you take yz to one side, so yz, you have yz here, this minus b1 yz you can take to this side, and remaining you have b2 yz z raised to minus 2 also you can take to this side, and that side you have xz plus a0 xz z inverse. That's all. So now yz by xz you can write as 1 plus a0 z inverse by, in the part of yz you have 1 minus b1 z inverse minus b2 z raised to minus 2. By taking yz outside from this and xz outside from this, and you take xz to this side and the portions remaining from to the denominator of this side, this become 1 plus a0 z inverse by 1 minus b1 z inverse minus b2 z raised to minus 2. So this is basically an FIR filter. So if you want, so suppose you want to implement this 1 plus a0 z inverse by 1 minus b1 z inverse minus b2 z inverse, what you have to do is you make delayed versions, delays here for xn. So this is basically 1, so that is reflected as a0. This should be a1. Let us put as a1 so that xn minus 1 the notations are correct. So a1 xn minus 1, a1 xn minus 1. So this become 1 plus a1 z inverse 1 minus b1 z raised to minus 2 minus b2 z raised to minus 2. Suppose you have some a0 here. In that case, you will have a0 xn plus, so that will cause instead of 1, you will have an a0 here. Okay, so let us put it as 1 itself. Similarly, if you have a b0 here, then our equation will change as yz by xz will become a0 plus a1 z inverse by 1 minus Instead of this, B0 minus B1 set inverse minus B2 set raised to minus 2. Okay. B0, am I right? Yn into, no, this B0 shouldn't be here, right? This B0 may cause confusion. So this B0 I'll leave out. So let this be 1 itself. This is 1 itself. Yeah. A0 minus. So if you have some DC term, that shouldn't be added here. So suppose you have you need to implement some filters like this: 1 plus A1 set inverse by 1 minus B1 set inverse minus B2 set inverse. What you have to do is you draw first the numerator part. So to implement the numerator part, you have to this you put as 1 and you put a delay. There's only one delay, and that is multiplied by A1. So you multiply it with A1. Okay. You add it together. Let this be here. And this part, 1 minus B1 set inverse minus B2 set inverse, these are all negative, right? So in this equation, you can see that yn minus 1, yn minus 2 go to the other side. So we'll have a negation in the coefficient. So this minus B1 and minus B2 will become plus B1 and plus B2. So whatever remains is, I'll do it here. Set inverse. You have an adder here. A1, you add it. Whatever comes here, this minus B1 and minus B2, you do a negation, and that become B1 and B2. And you put an adder again. Yn, from Yn you should take delayed version of Yn, which will be Yn minus 1, and that can be multiplied with the negated version of this. If this was 1 minus 3, you multiply it with plus 3. So you multiply it with B1 and you take delayed version. Sorry, delay is already here. You add it here. And again you take a delay. That gives you Yn minus 2. Yn minus 2 you multiply with B2 and add it here. B1, B2. So this gives the implementation that we have drawn here. Okay. So from a given implementation, you should be able to find what is the transfer function. Similarly, from a given transfer function, you should be able to draw, or you should be able to implement the hardware realization. So once you get this realization, this can be easily implemented in a hardware using just delays and multiplies and some connectors, right? So with this, we can get any desired frequency response for your filter. Now, the same thing you can do in some other way also, because this is basically your Y set or Y set is, you can write it as X set into H set or basically from this is H set is basically Y set by X set. This can be written as X set equal to Y set by some W set into W set by X set, where this will cancel. So what will be this W set? It will be the this frequency domain representation of the signal at this point. So from this, yz by the yz by wz will give the transfer function of this small region. Get the transfer function of this small region. So this region have a transfer function yz by xz. Similarly, this portion have a transfer function wz by xz. Okay. This portion has a transfer function yz by wz. So if you multiply these two, what you're going to get is yz by xz. So this way, this can be considered as two transfer functions. So you can, if this is, say, let us write this hz as h1, let's write this as h1z into h2z. In that case, if hz is h1z plus into h2z, this can be written as h2z into h1z by the property of our hz, the multiplication of two set transforms can be associated. What is this? Commutative, right? So what you can do is you can draw this figure, first this figure, then this figure. So our figure will be if you draw this first, what will be the figure? You have Z inverse and the Z inverse delay here. You have multiplier B1 and the multiplier B2, and these are added together here. These are added again here. And so this is the second portion that I drew first. H2 I drew first, and then I will be drawing the second one. This is having A0. We have the delay here. Delay, yeah, I think only one delay. With A1, you add it here. Then this is xn, this is yn. So this implementation should also give the same result as this. So this, okay, so you can, so the previous now you consider this point, particular point. Let us call this point P. You are taking from point, you are taking delay Z inverse to this region and Z inverse to this region. So these 2 points should also be the same. Let's call this P1 and P2. The signal at P1 and P2 should also be the same. So we can simplify this as these 2 delay as single delay. These 2 delays are single delay, and you take A1 to this side, B1 to this side. This A0 you can take from here, add it here, you take y of n. Here you have multiplied B1, again you add it here, add it with the x of n. This can be written as x of n. Again you take a delay. This delay can be multiplied with B2 to this side and add it here. So this is a simpler implementation of the same thing. So this become now simpler. The number of delays that you require is reduced now. So by reducing the number of delays, you get a better or efficient implementation. So these are called direct form 1 and direct form 2 implementations. In general, you call it direct form 1 and 2 implementations. Okay, so yeah, I think that's enough for today. Shall stop. So what we have seen today is the FIR filter implementation and IIR filter implementation, and how to make it. The implementation is using delays and multipliers. And given a transfer function, you should be able to design a FIR filter, or if it is an FIR filter, or otherwise an IIR filter. And given an implementation with multipliers and delays, you should be able to find the transfer function also. So that's what we have seen today. And if you have any doubts, you can ask now. I'll be stopping recording now.